welcome to Prep 101. If you weren't here yesterday, I'm Tina. So today we're going to carry on kind of where we left off. I'll go through a few things before we start though. So number one, any questions, you can post them on the Q&A as you're going through tonight. Anything technical, post those on the Q&A for Alicia. In your account, you have the booklet solutions, and the supplement. There's two parts, so if you did pick up a physical copy, some of them were printed and some of them weren't, just to save on trees. And so you have both of them in your account, as well as the solutions, okay? So under the dot cam, I'll show you what we did yesterday, as well as my email. So my email is on page 2, tinaresp@hotmail.com. So send me an email if you have any questions after the session. If you have anything that came up since yesterday, you can post it in the Q&A now. In terms of what we covered, so if you go back to page 1, the on-demand video, that's on all the midterm materials. So you can, watch as much of that as you need to, depending on, how well you did on the midterm and how well you understand each section. So yesterday we started with sensitivity, specificity, and type 1 and 2 errors, because that wasn't on your midterm this term. And then we covered up to, we were working on G, I guess, right? So that was session 1. And then today we're going to finish G and then obviously work till the end in our Zoom session 2. So I had said to you that the course has changed a lot yet again this term. It was actually kind of depressing today because I said I would go through the exams and write omit, get Alicia to help me write omit beside the questions you don't have to know. And there's a lot of questions that were really easy questions that now you don't have to know, which was a real bummer, I thought. Yeah, they did take out a lot of easy stuff like determining of a 3x3, dot product, cross product, finding the angle between two vectors. So all of those things on the exams you no longer have to know. So the supplement solutions looks like this. So the supplement's split into 2. So some of these are in supplement 1 and some are in supplement 2. But here are all the solutions. So there's obviously tons and tons and tons of practice here, right? So, do as much as you possibly can, obviously. The more questions you see off old exams, the better you'll know how to do things that they kind of throw at you this year. We don't really know how hard your exam's going to be. So, I know your midterm was fairly straightforward. So is your final going to be brutal to bring down the average? I don't know, right? It's hard to say. I do know that there's only been, I think, 1 or 2 times total in all the years I've been doing this course, which is a long time, that they said the final exam was easy. So that is one thing I do know for sure. So in this case, for you guys, no 3x3 inverse, no 3x3 determinant, which means no 3x3 eigenvalue eigenvectors, no dot or cross product, things like that. So I did get some clarification on the multiplying of matrices. So what they meant by that part of the message on L is that you're not going to have to multiply matrices, which is, again, unfortunate because it's a really easy concept. So you won't have to multiply, a 2x3 matrix by, let's say, a 3x4 matrix, right? You're not going to have that. But you will still have to do a matrix product with just a vector, okay? So for instance, if I show you what they mean by that, if you, have your supplement, the 2021-2022 final, the very first question says, which of the following vector matrix products are possible to commute? So they would be just looking at, you might have to do, let's say, a 2x2 with, let's say, that vector, right? So that kind of thing, you would have to know how to do. So when we get to Leslie matrices and you just do, juveniles and adults, and you figure out how many there are in the next stage, that would just be a matrix times a vector. So it would look like that, like this matrix times 1, 6 kind of thing, with the numbers, that might be decimals or whatever, depending on the question. Okay, so that we're going to do today. But otherwise, no multiplying a 2x2 by another 2x2, etc. Okay, so any questions before we start? We will take breaks if you weren't here yesterday. The video should be up sometime before the end of our session tonight. And tonight's video, sometime by the end of tomorrow night. Also in your prep account is now a printable equation sheet. So you can print that out, make cue cards, whatever it is that you need to do so you can, learn formulas the best that you can. Okay. And it's 5, so we'll take a break around 6:15 to 6:30, okay? Okay, so nobody's posted anything, so we will go back to, so we're going to go to page, let me figure out where we left off in the inverse section. So I suppose we can leave out powers now that I did get clarification on that. So if you turn to page 236, so if you were here yesterday, I'd said I wasn't clear, based on your notes, what kind of products you did and didn't have to know. So now you obviously won't have to know this, okay? So you can omit that. Okay, so middle of page 236 is where we'll start then, okay? Okay, so as far as inverse goes, so for any square matrix, we do know it has to be square. So 2 by 2, 3 by 3, etc. Okay, that's a square matrix. 2 by 2, 3 by 3, etc. We know that there's an inverse. If there's a matrix that when you take A times this new matrix, the inverse B, in any order and multiply, you get the identity. So remember the identity is, for a 2 by 2 down here, 1, 0, 0, 1. It has ones along the main diagonal and zeros everywhere else. So this would be a 3 by 3 identity. Ones on the main diagonal, zeros everywhere else. And so if it has an inverse, the inverse is denoted with a little -1 on the exponent. The inverse is unique, so there's only one inverse. If there's no inverse, you can say there's no inverse, or you can say it's not invertible. And the inverse, again, would have this property that if it multiplies by A in any order, you do get the identity. Okay? And remember, the identity is kind of like the number 1 for matrices. It means that when we multiply A by I in either order, we do just get the matrix A back again. Now, in terms of determinants, remember they've removed all the 3 by 3, right? So there's no 3 by 3s anymore. So the only thing you really would have to know about a 3 by 3 is, if you have the determinant, how do you tell if there's an inverse, okay? A 1 by 1 matrix determinant's just the number in the matrix. 2 by 2, so you talked about, you can do the determinant as AB minus BC. So 1 times 3 minus 5 times 2. So 1 times 3 is 3, minus 5 times 2 is 10, and that's -7. As long as it's not 0, then therefore matrix B is invertible, meaning it has an inverse. Okay, it has an inverse. So again, we can expand along any row or column to find the determinant of 3 by 3, but you don't have to know the process. So instead of saying, is this invertible, making you find the determinant, if they want to ask this in terms of what they gave you in the notes, it would have to be, here's the determinant. So for example, this determinant, this matrix is 48. And then they could say, is the vector field invertible? Or give you the determinant of a bunch of matrices and which one is or which ones aren't invertible type thing. So here, since the determinant's not 0, the vector field would be invertible. If our determinant is 0, then it wouldn't have an inverse. Okay. So for which value of k is the matrix invertible? If the determinant is defined as 3k plus 6. Well, we know that there's no inverse if the determinant is 0. So we can set this determinant equal to 0 and solve. So we would get 3k is -6, divide by 3, k is -2. So that would mean it has an inverse, or it's invertible, as long as k is not equal to -2. Okay, so k is not equal to -2, that's when it is invertible. Or we can say it's not invertible if k is equal to -2. Okay. So this would be like we're looking at the vector product that they were talking about that you would have to do. So, a matrix times a vector. A vector would just be one column here. So consider the non-invertible matrix. Okay, A. Find a non-zero vector x such that ax equals 0, the 0 vector. So if you go to do a product, you're just going to take a row and you're timesing by this column. So we did it yesterday. It would be 2 times x1 plus 1 times x2 plus 1 times x3, and that would equal the top 0. And then you would take the middle. It's actually called the dot product, but you don't have to know that. So it's negative 2 times x1 plus negative 2 times x2 plus 2 times x3 equals the middle. And then for our bottom row, 1 times x1 plus 0, don't really need 0, plus 2x3 equals 0. So there's all the equations. So how we solve it? Well, this one's probably the easiest one because it only has 2 variables. So we could say that x3, we could move this across and say 2x3 is, 2x3 is negative x1. So then x3, divide both sides by 2, negative a half x1. And then I can sub this back into here. So I've got this equation, negative 2x1 minus 2x2 plus 2x3, but I'm going to put the x3 right here as negative half x1. So now I can multiply this out and collect my like terms. And I've got, negative 3x1 is, if I bring that across, 2x2, and then we can solve for either one. I solve for x2 in terms of x1. The reason why I picked to solve for x2 instead of x1 is see how x3 is given in terms of x1? And so this is, x2 is in terms of x1 as well. So then what's my vector? x1, x2 is going to be negative 3 halves x1, and x3 is negative 1 half x1. Okay, and so this is kind of like what we're going to do, when we get into eigenvectors, right? We can write this as 1, negative 3 halves, negative 1 half times x1. Or we can call it a t, or something like that. Okay, so when we get to eigenvectors, we'll talk about, how you can have any multiple of this, right? We could multiply all the components by 2 to get rid of the fractions, and that would be an equivalent vector. So, number 14, on the top of 239 here. So if we've got A and we want to find AX, well, so all we're doing here to find A times vector X, again, so this would be what they mean by a matrix vector product as opposed to matrix, right? So this vector is just one single column. So go ahead. What would be your top row here if you do this dot this? Okay, first times first plus second times second is what you're thinking there for the vector. So negative 3 times 1 plus 5 times negative 3. So negative 3 plus negative 15 is negative 18. Okay, what would your bottom row give you? If you do the bottom row of A and then times by this vector X. Again, first times first plus second times second. So we'd have 1 times 1 plus 2 times negative 3. And again, I did show you dimensions, so you do know that you can do this, and your answer is a 2 by 1, which means, 1 column and 2 rows, right? And that's obviously what we got. So this is 1 minus 6 is negative 5. Okay, so that's the only kind of product you're going to have to do. So here, if I wanted by, and I want the third entry, then I just be taking the bottom row, the third row, and timesing by this vector y. So the third entry would be what? First times first, plus second times second, plus third times third. So let's see, 0 times 1, plus 4 times 0, plus 2 times negative 1, and that would just be negative 2. Okay, any questions? Okay, so again, not much to know in that section anymore. H is another quiz. So you've got mean, variance, vector fields, etc. in that section. So look at page 244. So matrix models, and I know they didn't call them Leslie matrices, but I'm just used to calling them that. So this is when we're looking at, the survivability of a species, right? So page 244. Okay. So when we call it a Leslie matrix, it shows us the survivability and fecundity information about a species. The number of offspring is the fecundity. The survivability is the proportion of a certain population that survives from one season to the next. So if we interpret the following matrix based on 100 hatchlings and 200 adults. So the first number is H for hatchlings, and then that's adults. Okay, so we have H and A. And then when we look at this, it's also H and A on the top. And we read from the top down the side. So this 0.8 is hatchlings to hatchlings. This 0.6 is hatchlings to adults. This 1.2 is adults to hatchlings, and the 0.5 is adults to adults. So the first number here, the 0.8, when I say hatchlings to hatchlings, then that means that we're looking at, if there's 100 hatchlings this year, we expect 0.8 times 100 or 80 hatchlings next year. If we look at the 1.2, what does that mean? Adults to hatchlings, 1.2. Well, that means that's the fecundity offspring of the adults, right? Adults producing hatchlings. So up here it tells us there's 100 hatchlings and 200 adults. So if we have 200 adults and adults to hatchlings is 1.2, then we take 1.2 times 200. And that means there's going to be a total of 240 hatchlings next year from this current year's adults. So that's those two. And then if we look at the 0.6, hatchlings to adults is 0.6. Hatchling to adult means, what percent of the hatchlings are going to survive to become adult. So 0.6 is the survival rate. That means 60% of the hatchlings will actually survive into the next year to become an adult. So if there's currently 100 of them, then 0.6 times 100 is 60 that will survive to actually become adults. The 0.5 is adult to adult. What's that mean? Well, that's the adult survivability. So that means that 50% of this year's adults will survive to become, next year's adults. And if there's 200 right now, then half of 200 is 100 in the next year. So you can do each of these numbers separately, or you can look at the matrix, the H and A matrix times the vector for 100 hatchlings and 200 adults right now, and, do the product like I showed you in the other one, right? So 0.8 times 100 plus 1.2 times 200, and that's our 320. And on the bottom, 0.6 times 100 plus 0.5 times 200, which are the numbers that we did up here. So we'll have a total of 320 hatchlings and 160 adults, okay, in the next year. So number 2 here, suppose there are beta 1-year-old female ducks and gamma 2-year-old female ducks. So beta are 1-year-olds, gamma 2-year-olds. Each of the 1-year-old females produce 6 offspring in a season, and each of the 2-year-old females produce 7 offspring. If X is beta gamma and Y is 0,7, then what does this product represent? So if we take beta gamma and times by 0.7, well, like we said before, first times first plus second times second is only going to be gamma times 7, or 7 gamma. What's 7 gamma? What do you think that means? Well, if gamma is the number of 2-year-old female ducks, and look at 7 is the offspring of, right, 7 offspring for each 2-year-old duck, and gamma is the number of 2-year-old ducks, then what's this represent? Well, the number of 2-year-olds times the offspring is going to be the total number of offspring, right, produced by female ducks here. So it would be C. So if we wanted the total offspring of all the ducks, then we would have, 6 for each female 1-year-old. So it'd be like 6 beta plus 7 gamma would be our total of both 1 and 2-year-olds. Okay. So here we've got a population of birds with Leslie diagram given below. So we've got H for hatchlings, A for adults. So in terms of this diagram, sometimes they called it a matrix diagram or a network diagram. So many words for the same thing. Basically, you've got a picture with arrows, right? And so from the picture with arrows, you want to make a matrix, okay? So let's take a look. This arrow going around from H to H is asking for hatchlings to hatchlings. So let's think about that. Let's write our matrix here just so I can do it right beside. So HA, HA, remember we're reading from the top down to the side kind of thing, right? Okay, so hatchlings to hatchlings. Well, that's 1.2, right? Hatchlings to hatchlings, 1.2. Now here, hatchlings, the arrow's going to adults. So hatchlings to adults. Put that where it would go in your diagram here, in your matrix. So from H to A is 0.5. Where would that go here? H down to A, right there. Now A to A, so that's adults to adults. So this year's adults, right, living to be there for next year's adult. So put your 0.3 in where it would go. So that's A down to A, so that would go in the bottom here, 0.3. And then this one, A to H, is adults producing 1.5 hatchlings each, right? Adults, the arrow's going to hatchlings, so adults to hatchlings. So that's our matrix. And if we want to find the number of hatchlings in year 1, if we assume that at time 0, there's 100 hatchlings and 50 adults. Okay, so then we want to take our matrix. And again, of course, you can find this answer without actually doing a matrix times a vector, right? We could do, each of them separately, like I did at first in the last one. So you're not required to do the product by matrices, but it's certainly a lot faster, right? So we just take row with what we call dot column, which remember is really just first times first plus second times second for each of these rows with the vector, right? So let's see, 1.2 times 100 plus 1.5 times 50. Okay, write down what would your answer be for the bottom row, representing the adults. What would it be? So we get first times first, 0.5 times 100 plus 0.3 times 50. Okay, so that means that we've got 1.2 times 100. So move your decimal twice. So that'd be 120 plus 1.5 times 50. So 1 times 50 is 50, and then a half of 50 is 25. So we're really just saying plus 75. So that's 195, and that's how many hatchlings that we would have in the next year, right? In year one. Okay, now we have half of 100, so 50, plus 0.3 times 50. So 3 times 5 is 15, right? So 0.3 times 50 is 15. Okay, so in general, we can say with xt and xt minus 1, or we can say xt plus 1 and xt is this A matrix times the one before it, right? We're taking the A and we're taking, this kind of like XY vector, right? And that's how we got this answer. Okay. So we basically did X1 is A times X naught. Questions? Now you can work between the various methods. So I'm going to show you this one, even though it's a 3x3, just to show you percentages, because a lot of times they'll try and trick you on the exam. So even if they only give you 2x2s, I still want you to get the concept here that if they tell you what percent something is dying at, you don't want to use that percentage, okay? You always want to use the percentage that survives. So make a note of that, because that can be confusing to people. So when you go to make your matrix, always think surviving numbers. So this time the population has hatchlings, juveniles, and adults, but the concept's exactly the same. So here where it says 50% of hatchlings die each year and the rest survive. So we want to say 1 minus 0.5 is 0.5 of the hatchlings survive to become juveniles. Okay, we always want their surviving numbers in our matrix. So hatchling to juveniles, 0.5. Okay, 60% of juveniles die each year. The rest become adults. Okay, so think about that number. 60% of juveniles die, the rest become adults. So fill that in your matrix, what you think it would be here. So 0.4 is the number that survive, right? Juveniles to adults would be down here. So 0.4 survive. Adults do not survive further years. So adult to adult, 0. That's depressing. Okay. And hatchlings don't produce hatchlings next year. So where does that go? Hatchlings to hatchling, 0. And each juvenile produces 0.2 hatchling the next year. So each juvenile produces 0.2 hatchlings the next year. So fill that in. So juvenile to hatchlings, that'd be there. And the last one, each adult produces 1 hatchling. Adult produces 1 hatchling. So adult to hatchling 1. Anything they don't tell you, you just fill in zeros. Okay? So anything that's unknown is zeros. So what if you took this information and you wanted to draw, instead of the matrix, the actual diagram here? Well, make it hatchlings, juvenile, adults here. So we had hatchlings to juvenile, so draw the arrow towards juvenile, that's 0.5. And then we have juvenile to hatchling is 0.2. So that goes backwards. So that's those two. And then we have adult to hatchling is 1. Okay, draw that in. So adult to hatchling is 1. Okay, and where would the 0.4 go here? So that's juvenile to adult. So juvenile to adult. And I mean, technically, you don't really need to put any zeros in, right? Because they're never going to change anything in terms of your answers. Okay, so estimate the population of hatchlings and adults in years 2 and 3 if there are 50 birds in the population consisting of 30 hatchlings, 10 juveniles, and 10 adults. Okay, so we know that, our vector is going to be this matrix times the vector before it. So it's going to be the A matrix times the one before it. So at the start, I have 30, 10, and 10. So if I have this matrix, again, if you don't want to do the product, you can do it like I did the long way in the first one. It's just going to be a lot more work, right? So this is like our x naught, and so this is like our x1, right? And you can think of it as, I guess they said year 2, so you could also think of it, it's just, using the one before it. So you could also call this, if you wanted, year 2 is, the A times year 1, right? So whatever numbers you want to use, as long as you know you have to do it twice, right? Because what we have here is considered year 1. So let's do this. So we have 0 times 30 is 0, plus 0.2 times 10. 0.2 times 10 is 2, plus 1 times 10 is 10. So that's 12. And then we've got first times first, plus second times second, plus third times third. So half of 30, half times 30 is 15, plus 0 times 10 is 0, plus 0 times 10 is another 0. Okay, what's your bottom number going to be? I'm just going to write out what this, oops, I wrote 0 here. 15 plus 0 plus 0, 15. Believe me. Okay, too busy looking at the zeros. So what's this row dot the vector? So 0 times 30 is 0, plus 0.4 times 10 would be 4, plus 0 times 10 is 0. So that means at the end of, year 2, if we call it that, there'd be 12 hatchlings, 15 juveniles, and 4 adults. So if you want to do year 3 now, we want to call it, let's say, x3, we still need our original matrix, but we're not going to take the 30, 10, and 10. What are we going to have to use? Remember, it's recursion, so we've got to use the one before it. So what happens is these numbers go down in here. We take the year 2. And so it's 12, 15, and 4. And then we would multiply to get that. Okay. So let's see. 0 times 12, 0, plus 0.2 times 15. So 2 times 15 would be 30. So 0.2 times 15 is 3. plus 1 times 4. So that's going to be a total of 7 hatchlings. The middle one's all zeros except for 1, so that's nice. So a half times 12, half of 12 is 6, plus 0 times anything plus 0 times anything. So that's juveniles. And how many adults? Well, we'd have 0 times anything is 0, plus 0.4 times 15, so that's, well, 4 times 15 is 60, so that would be 6, and then plus 0 times 4 is 0. So 7 hatchlings, 6 juveniles, and 6 adults. Now, if you notice the numbers, they're getting smaller, right? 30, 10, 10, 12, 15, 4, 7, 6, 6. If you keep doing it, then look at what's happening, right? The numbers are getting smaller and smaller and smaller. So what accurately describes the long-term behavior of this bird population? The total population is decreasing to nothing, right? So decreasing to 0. So if we look at, let's say, this one on page 250, what would, if you look at this matrix, what would the network or transition or matrix diagram look like if you do it as a diagram with your circles? Just how do you practice some of those? Okay, so if we have hatchlings and adults, so here we're saying hatchling to hatchling, so that's a 1. Hatchling down to adult, that's a 3. Adult to hatchling, adult's producing 5, and adult to adult is 0. Okay, so that's what we're looking at in terms of section I. Any questions? Okay, so we're going to move into eigenvalues, eigenvectors, okay? So page 253. Okay, so, you might be asked what's called the characteristic polynomial, or finding the eigenvalues, or finding the eigenvectors in this section, okay? So the characteristic polynomial, again, you guys are only doing 2 by 2s. So it's going to be using the equation determinant of a minus lambda I equals 0. It's going to be a polynomial with, instead of x's, like x cubed, x squared, those are polynomials, right? In terms of this example, it's going to have lambdas, this Greek letter, okay? So, and the lambdas will end up being what we call our eigenvalues. So there's a little shortcut if you want it for multiple choice that I'll show you. So of course, don't use it for long answer, but a lot of, these questions will be multiple choice. It's highly unlikely they'll just ask you for eigenvalues and a long answer, right? Probably not. So if you want, you can also do the trace of A, so the trace of the matrix, A plus D. The determinant, which we already know, is AD minus BC. And then this would be our formula. Lambda squared minus the trace of A times lambda plus the determinant equals 0. And your matrix here is, of course, as always, A, B, C, D. So here, method 1, if we want to use det A minus lambda I equals 0, here's our matrix A, 4, 3, negative 2, negative 3, minus lambda times the identity. Identity for 2 by 2, remember, 1, 0, 0, 1. So really this is 4 minus lambda, and then 3 minus 0 is 3, and negative 2 minus 0 is negative 2, and negative 3 minus lambda is negative 3 minus lambda. So if we go to do the determinant of this, we do A times D minus B times C. So AD, we take 4 minus lambda times negative 3 minus lambda. So we can FOIL that out. First outside, inside, last. That's AD. Minus, and then this way for BC, we would just get minus a negative 6, so plus 6, right? So here, if we FOIL it out, we get negative 12 minus 4 lambda. On the inside, a plus 3 lambda. Negative times negative, so plus lambda squared plus 6. Collect your like terms, collect your lambdas, collect your constants, and that's your characteristic polynomial. And to solve for the eigenvalues, we would factor. So another way to do it for this matrix, if you want something that's a lot quicker, is A, B, C, D here. So the trace is we just add 4 plus negative 3. That's 1. The determinant AD minus BC is negative 12 plus 6 is negative 6. And so your formula is just lambda squared minus the trace times lambda plus the determinant. So lambda squared minus 1 lambda, and then plus the determinant, so plus negative 6. So it's the same thing, it's just less algebra, that's all. So some people prefer it just to save on the algebra they have to write. So if you're one who doesn't like algebra, you might prefer that for your multiple choice. Okay. So after you find the characteristic polynomial, then you just factor it to find the root. So I suppose you could get a trinomial, a common factor, difference of squares, any of your factoring types, right? So this was our answer on the last page to the characteristic polynomial. So if I factor this, I'm looking for numbers that add to the middle, which is negative 1, and multiply to the last term, which is negative 6. So numbers that add to negative 1 and multiply to negative 6 would be negative 3 and positive 2. Okay, and there's our factors. So what do we get? Well, if this is 0, then lambda is 3, and if lambda plus 2 is 0, lambda is negative 2. So those are what we call our eigenvalues. Okay, eigenvalues. Questions? Okay, so let's do it. A, B, C, D. Find the characteristic polynomial. Okay. So method 1 for multiple choice. Well, the trace is A plus D. 2 plus negative 1. 1. Det A, AD minus BC. All right, go ahead and do your determinant here. So AD, 2 times negative 1, minus 3 times negative 2. So that's negative 2 plus 6. Negative 2 plus 6 is 4. Okay, so what's our answer? Well, it's lambda squared minus the trace times lambda plus the determinant. So lambda squared minus the trace, minus 1 lambda, plus determinant. Of course, you don't need the 1. I'm just emphasizing that it's minus whatever the trace is. So that's our characteristic polynomial. And by the way, some people, instead of setting it equal to 0, will just call it f of lambda. I usually just set it equal to 0 because they never just ask that, right? You always have to factor it after. So then you need equal to 0 anyway. So I kind of just skip a step there. Okay, so method 2 for long answer, or if you don't like the trace method, would be det of A minus lambda I is equal to 0. So we take our matrix A, which is up here, 2, 3, negative 2, negative 1. 2, 3, negative 2, negative 1. Now, whenever you do lambda times I, let's think about it. Lambda times I is really just going to be the lambdas on the main diagonal, right? Because anything times 0 will always be 0. So you're really always going to get this. So if you want to skip a step, instead of writing lambda times I, just write the lambda where the 1s are on the main diagonal of the identity. Kind of like that, okay? So what would our det be here? Well, a matrix minus a matrix. So just subtract the numbers in the same spot. So 2 minus lambda. 3 minus 0 is 3. Negative 2 minus 0 is negative 2. And negative 1 minus lambda is there. Now, of course, we all know that determinant of a 2 by 2 is going to be AD minus BC. And so we get AD, so 2 minus lambda times negative 1 minus lambda minus BC, 3 times negative 2 equals 0. All right, go ahead. I want you to FOIL this out. Watch your signs and collect your like terms and see if you get the same answer that we had, okay? Okay, so we've got 2 times negative 1, so negative 2 first. Outside, 2 times negative lambda, negative 2 lambda. Inside, negative times negative, so that's plus a lambda. And last, negative lambda times negative lambda is plus lambda squared. This would be plus 6. So we've got a lambda squared. Let's see, we've got negative 2 plus 1, so that's minus 1 lambda. And then 6 minus 2, so plus 4. So again, same answer, just a different way to get there, right? Okay, before we go and do, lots and lots of examples of eigenvalues and eigenvectors, we're going to talk a little bit about complex numbers just because they did put that in the notes. And, it's potentially a question where they'll just ask something about complex numbers just because we are going to study complex, roots of equations, okay? Any questions about this before I flip? Okay, so definition of a complex number is on the top of page 255. Okay, so if we see the square root of a negative number, well, the square root of negative 1 we just defined to be I. If we square both sides of this, we would say that I squared is going to be negative 1. So if we end up with, when we're solving shortly, if we end up with, let's say, square root of negative 16, we could think about that as square root of 16 times square root of negative 1. Remember, the root of AB is the same as root A times root B. That works for product and quotient. It does not work for sum and difference. So just for multiplying and dividing, it works. And then we could say the square root of 16 is really just 4. and we define the square root of negative 1 to be I. And so that would be our answer. So in terms of a complex number, there's no real part here. So it's like 0 plus 4I. So A is what we call the real part of a complex number. And the B, which is 4, the number in front of the I, is called the imaginary part of the complex number. Okay? So when we go to talk about complex numbers, we kind of like to write them as A plus or minus BI. So often they'll use the letter Z to represent a complex number. Z is A plus BI. A is the real part. Some people, instead of writing the word real, will write RE for real. And then B is the imaginary part. And again, some people will shortcut it as IM for imaginary instead of writing the word imaginary. The complex conjugate of A plus BI is A minus BI. So we use Z and then Z with a bar over it. And what we'll need the conjugate for is something like this. If they say, here's a fraction and express it in the form A plus BI, then we want to get rid of the bottom. And it's kind of like in calc where, we have that root, a root plus a number and we multiply by the root minus a number. It's the same kind of thing. That got rid of the square root. This is going to get rid of, these terms from the bottom so that there'll be no I terms left. So we take the original question right here and we multiply by the conjugate of 3 plus 7I. So here we're looking at, our Z is that, and our conjugate is 3 minus 7I. And that's what we're going to multiply by on the bottom. Of course, if we multiply by a term on the bottom, we've got to do it on the top, or otherwise we're going to change our question. So then we FOIL it out. So the top, negative 2 times 3 is negative 6. Outside, negative 2 times negative 7 is plus 14I. Inside, 3I times 3 is 9I. And last, 3 times negative 7, so that's negative 21. And it's I times I, so it's I squared, which we'll talk about in a sec. On the bottom, when we FOIL, 3 times 3 is 9. The middle, so the outside and the insides will cancel because we get negative 21I and plus 21I. And that's the whole point, right? Getting rid of those I terms. And then the last term is plus 7I times negative 7I. So negative 49I squared. Now remember, if I is the root of negative 1, then I squared is just equal to negative 1. So what we're going to do is we're going to substitute. Anytime we see I squared, we put in negative 1. So this is negative 6 plus, if we add these two, we get plus 23I minus 21 times negative 1. And the bottom, 9 minus 49 times negative 1. And then we just add up the like terms, right? We've got a negative 6 and a plus 21. So we really got 15 plus 23I on the top. And be careful of your signs. That's really 9 plus 49. So this is our answer. If we want it as A plus BI, then we'll just write 15 over 58 plus 23 over 58I. And this now has the form A plus BI, right? So our A is the 15 over 58, and the B is the number in front of I, so 23 over 58. Okay? Questions? Okay, find the sum, product, and difference of these. So sum just means add them up. So that's easy. We can just add the like terms, right? So 5 plus negative 2 is just 3. And negative 3I plus 8I is 5I. So that's the sum. For the difference, just remember that it's subtract. So it's really negative 1 times everything in the second bracket. So the first bracket, it's just going to stay the same. It's just going to be 5 minus 3I. But then we do negative 1 times negative 2 is plus 2. And negative 1 times 8I is negative 8I. And then we can just collect like terms. 5 plus 2 is going to be 7. And then a negative 3I and a negative 8I is going to add up to negative 11I. Okay, and the last one for the product, well, that's just kind of like what we did in the last example 3, right? So FOIL, so negative 10 plus 40I plus 6I. and then the last term will be minus 24i squared. And then, of course, you're again going to substitute that I squared is negative 1. Collect your like terms. Okay, so we get negative 10 plus 40i plus 24. So 24 minus 10 is 14. And then, oh, there should be plus a 6i here. Looks like my 6i disappeared. So 40 plus 6 would be 46i's. Okay. So that's kind of the basics of complex numbers there, okay? Okay. So the absolute value or modulus of a complex number, what's that? Well, the absolute value or modulus is the distance from the origin, okay? So if we see complex numbers, that is a plus bi, the modulus or the absolute value is just going to be the square root of a squared plus b squared. So if we want the absolute value of 4 plus 5i, well, my a is 4 and my b is the number in front of the I. So z, absolute value or modulus, is going to be the square root of a squared plus b squared. So square it out and you get root 41. Right? 5 squared and 4 squared. So basically 16 and 25 square root 41. And for any complex number, so they had put this in your notes this year. If you do want to memorize it, then 1 over z is 1 over a plus bi. And so you can multiply by a minus bi on the top and bottom. And this would end up being your answer for 1 over z. The real part would be a over a plus b squared, and the imaginary part would be negative b over a squared plus b squared. Okay, so let's go back to eigenvalues for complex. So by the way, this, you can do the long way. So remember we had a 4 plus 5i from example 5. So if you wanted to do, if they asked you to do 1 over z, you could do 1 over 4 plus 5i. But then they're saying if you don't want to work it out, you can just memorize that the real part would be this and the imaginary part would be that. But you could also just do it the way we did on the last one, right? Multiply by 4 minus 5i, because that would be the conjugate of the bottom. So FOIL this out would be what? 16 minus 20i plus 20i. 5 times negative 5, so minus 25i squared. So that would be 4 minus 5i over I squared. Well, how about you finish this? Think about what your I squared is and fill in your bottom here. Well, if that's negative 1, then we get 16 minus 25 times negative 1, which is 41, which is like 4 over 41 minus 5 over 41i. Okay, and so they're saying you could, instead of working that out the long way, you could just say, well, a is 4, b is 5, check it. 4 over 4 squared plus 5 squared, right? So that's the real part. So the real part is a over a squared plus b squared. Does that work? A is 4. 4 squared plus 5 squared is 25 plus 16, isn't it? So see how it's the same? That formula and doing it the long way, okay? And then negative b, so that's negative, and then yes, 5 over 41. Okay, so kind of long way versus short way, I guess, right? So do you want to memorize something else? There it is, okay? Any questions? Okay, so find the eigenvalues for example 2. So this was the characteristic polynomial we had a little while ago now because we kind of took a detour to complex numbers, right? But we have our quadratic formula, which is normally x equals, but now it's going to be lambda equals. So if we think about the numbers in front of this, I'm just going to emphasize here, the number in front of lambda squared, there's nothing there, it's a 1. The b here is a negative 1, and the c here is 4. So lambda equals negative b. Well, negative 1 is positive 1. Plus minus square root b squared. I always just like to square it out. So negative 1 squared is clearly just 1. So just square it. Minus 4 times a is 1 times c is 4 all over 2 times a. So you got 1 plus or minus. Now look under your square root. 1 minus 16, so that's negative 15. So that's why there's an issue, right? Which is kind of why I sidetracked to complex numbers. So think about the root of negative 15 as the root of 15 times the root of negative 1. Can you simplify that based on what we just talked about the root of negative 1 here? So this is our I, right? So it'd be 1 plus or minus root 15I. So if we want to see our two roots, one of the lambdas is 1 plus root 15I over 2. And the other lambda is 1 minus root 15I over 2. When you have complex eigenvalues and not real, these two numbers will always be conjugates of each other. So it'll always be, the plus and then the minus in between them. Okay, so these are what we call complex conjugates. So if they ever give you one root of a complex, is a plus bi, the other one's just a minus bi. Okay, any questions? Okay. So on to eigenvectors. So once you have the eigenvalues, then you can find the eigenvectors. So if we look at a minus lambda I times v equals 0, that's the one to use. It's easier for complex roots. You can also use av equals lambda v. Now, either one can be used anytime, so it's really just a personal choice, to be honest, right? Now, when you go to solve, maybe you have eigenvalues 3 and 2. 3 gives you an eigenvector, 2 gives you a different eigenvector, right? If you end up with, when you go to solve an equation, let's say you end up with 0v2 equals 0v2. Be careful. This does not mean that v2 is 0. Okay, it's a very common mistake. So this does not mean to let v2 as 0. Okay, so we'll see that in our solutions. So just be careful, okay? Now, here I had matrix A, and here are my two eigenvalues. So 3 and negative 2. So if I put negative 2 in, so I'm using this A minus lambda IV. So A minus negative 2 is plus 2 times I times V equals this 0 vector. If I add up, this is really just going to be 2's here, isn't it? So 4 plus 2 is 6, 3 plus 0 is 3, negative 2 plus 0 is negative 2, negative 3 plus 2 is negative 1. And if I go to do this, just like we were multiplying before, a matrix times just a vector, first times first, plus second times second. So 6v1 plus 3v2 equals 0. From the bottom, we get negative 2v1 minus v2 is 0. Well, if we go to solve this, well, we can solve either one, it doesn't matter. But if we're looking at this, if we've got negative 2v1 minus v2, bring the v2 across, and that's really v2 is negative 2v1. So what that means is the second component of the vector is negative 2 times the first component. So you can write your vector, v1, v2, you can write it as, for instance, v1, and then v2 is negative 2v1. And you can call it, some people will say v1 in front of 1, negative 2. I think you guys used a t a lot of the times, this term, right? T times 1, negative 2. This is the eigenvector that goes with that lambda, which was negative 2. Okay, so that's the corresponding eigenvector for eigenvalue negative 2. And of course, when I write the t here, t is any real number, right? So it can be any multiple of this. So guess what? If you gave the vector as 1 times 2 is 2, and 2 times negative 2 is negative 4, so you gave it as 2, negative 4, it would be an equivalent answer, okay? So a lot of times people will say, the family of eigenvectors is some constant c, t, whatever letter you want to use, times 1, negative 2, okay? So sometimes we get the same equation twice, which if I solve this one, I get the same thing as I got here, right? Because if I divide both of these equations by 3, then it'd be a 2v1 plus a v2, which is equivalent to this, okay? So sometimes both equations are the same thing. Sometimes one equation will give you, v2 is 0, okay? But again, just be careful of if you get 0 v2 is 0 v2, that's not the same thing, okay? So just beware. Now, there's a little trick that one of the TAs used to use years and years ago, that it's obviously only for multiple choice, but, you probably will get some eigenvectors on your multiple choice. And so eigenvectors are going to be any non-zero multiples of either b over lambda minus a or lambda minus d and c. So if your matrix, we always called your matrix A, B, C, D, and lambda is your eigenvalue. So if your lambda is your eigenvalue and you do b over eigenvalue minus a, b and a are from this, if you get the 0 vector can never be an eigenvector. So then you would switch to this formula, your eigenvalue lambda minus d over c. And that's just a quick trick that gets you it without doing all that work. So just keep in mind 0, 0 can never be an eigenvector. Okay, now keep in mind for this that you can only ever get one eigenvector. So this works great if you have, lambda is 2, lambda is 3, or lambda is 3 and 5. Great, you can use these methods. But it's not going to give you 2 vectors. So if you get an example, so for example, if you get lambda is both 2, right? In other words, eigenvalue 2 twice, what we would call like a double root in high school, then you can't use the shortcut. Because we don't know, just by looking at this, we have no idea. Is that one eigenvalue going to give me 2 different eigenvectors or 1? Well, this method can only ever give you 1, okay? So we have to do it the long way because we can't tell if we will end with 1 or two eigenvectors.